Speed. What does it take to fly faster than sound?
They were very violent. It makes the airplane buck around and bang your head around.
To reach 300 miles per hour in just a few seconds. Speed. How fast is the fastest gun in the West? And what does it take to be the fastest horse on the track? It's all about speed. New York's Lebanon Valley Dragway. Today's a day for everyone from backyard mechanics to the pros to experience speed. But the top attraction for the crowd is the fastest racing machines in the world. The Top Fuel dragsters and their superstar drivers like Shirley Muldowney.
I think, personally, it's the sound of the motors. It's the sound. And it's not noise, it's sound. Two cars sitting on the starting line, ready to launch, is a total of about 10,000 horsepower. When they leave the starting line, the ground actually shakes. If you can imagine from a dead start through the quarter mile, 1,320 feet, under 5 seconds, speeds up to 300 and over 300 miles per hour. I can't even start to tell you. A lot happens out there in less than 5 seconds.
Shirley Muldowney is a legend in racing, a 3-time world champion, and the first woman to earn a Top Fuel license. Her career started here at this dragway. This evening's challenge match pits her against Doug Herbert, also a 3-time world champion, and this track's record holder. Top Fuel dragsters combine brute force with delicate design to achieve fantastic acceleration from 0 to 100 miles per hour in a little over a second, 300 miles per hour in under 5 seconds. With their ear-splitting roar, the engines would seem to hold the key to such speeds, but that's not the case.
Well, these Top Fuel cars have so much horsepower that horsepower is almost not even a factor because you just can't use that much horsepower. So getting as much power to the tires as you can possibly use without spinning the tires is the whole trick.
It's not the engines, but the power applied through the tires that creates maximum acceleration. And that's true for every class of dragster. The contact patches, the 2 areas where the rear tires touch the ground, must transmit the force of these magnificent engines in a space the size of a briefcase. Even the rituals of the start, observed by both the pros and the amateurs, are largely about getting the tires ready. First, it's a trip through the water box to get the rear tires wet. A wet tire is easy to spin in the burnout. A burnout cleans the tires and creates more traction by leaving a clean patch of rubber that adheres to the now hot and sticky tires. One of the secrets to going fast, in fact, a key breakthrough, was the work of this man, Marvin Rifkin, at the time a local tire recapper, the M in M&H Tires. A familiar figure at the drag strip, he answered the driver's call for more traction.
We had to do something to try and get more. More bite, more bite, more bite. That's all you hear from a driver. I need more traction, more bite. Well, you put two and two together and say, that's how I got to get more bite.
Marvin Rifkin's innovation remains at the heart of racing tire design and can be seen in many of the tires used at today's event. His was the first wrinkle wall tire, a tire with a thin sidewall.
When you make a sidewall with less ply, the tire, squat tire, wrinkles. And as you rev the engine and hold the clutch in, the tire starts to turn like this. And you get all these wrinkles on the tire. That's a wrinkle wall.
The tires are basically like a rubber band. When you take off, the tires wind up, and then they unwind, which springs the car out. And also, as the car is going down the track, the sidewall being kind of flimsy will take and the centrifugal force of the tire spinning at a higher speed will cause the tire to, to pull in and to get taller.
Growing the tire allowed for full traction at the start and effectively a new higher gear at the finish.
And the distortion of this tire, you'd swear it's coming right off the rim. But sitting in the seat of the car, I mean, it feels as smooth as a Sunday ride down there in the lights.
Tonight's Sunday ride is about to begin. Strapping the drivers in, Muldowney in her dragster and Herbert in his, is the last act in a long series of preparations for the race. Both teams have spent the past 80 hours getting ready for the next 5 seconds. With a tip of the helmet, Muldowney pulls up to the final staging lights.
Ladies and gentlemen, I suggest you get to your feet and start making some noise for the driver who just set a new track speed record here at the racetrack at which she began her drag racing career, Shirley Muldowney. It's back to the
Muldowney sets a track speed record, traveling at almost 290 miles per hour by the end of the run. But near the start, the disappearance of her exhaust flames reveals she had to take a moment off the accelerator to allow her spinning tires to regain their grip. Herbert wins in what seems like a flash.
Going down the track 5 seconds, it seems like it's an hour. But like Albert Einstein says, you talk to a pretty girl for an hour, and it seems like a minute. You put your hand on a hot stove for a second, it seems like an hour. That's about the same way as it is driving one of these things.
More than 30 years ago, a revolutionary aircraft took off from a top-secret airfield somewhere in the Nevada desert. Back then, the SR-71 Blackbird was the fastest jet airplane in the world. It still is. Speed. What does it take to fly faster than any other?
All of our increases in speed of travel have been done in the atmosphere. Even getting to orbit, you have to go through the atmosphere. Now, the atmosphere objects to that. The atmosphere is a fairly dense, sticky stuff, and it objects to things going fast through it.
And the objections increase with speed. In the 1940s, as experimental aircraft approached the speed of sound, they encountered an invisible barrier in the sky. It tore the wings off and killed pilots. They called it the sound barrier. As a plane pushes through the air, it causes minute pressure disturbances to radiate away, like the ripples on a pond. At low speeds, they outrun the plane. But when it accelerates to Mach 1, the speed of sound, the ripples pile up to form a large standing wave, a dangerous zone of high drag and pressure, a barrier to speed that stymied engineers and pilots alike.
Well, the sound barrier was one that that we thought we could get through because we knew that bullets traveled at supersonic speeds and artillery shells.
So we knew things could go faster. Shooting a muzzle velocity on a 30-06 rifle bullet, that thing comes out of there rotating and is stabilized by the rotation, and it goes supersonic. So we knew it would be possible if you could get enough thrust and if you could reduce the drag.
In 1948, a tiny rocket plane specifically designed to break the sound barrier was rolled out onto a remote airfield in the high California desert, the Bell X-1. The hydrogen and oxygen fuel in her 4 rocket engines gave her 6,000 pounds of thrust. With fuel for just a 2.5-minute burn, the X-1 was carried aloft, strapped to the belly of a B-47. Chuck Yeager, the aircraft's pilot, would be flying into the unknown. Could the X-1 survive the turbulent air as it approached the sound barrier? And what would happen once the barrier was penetrated? Entering a danger zone of speed at Mach 0.96, Yeager encounters buffeting. But trusting his tiny aircraft, he presses on toward Mach 1. At Mach 0.98, the X-1 shakes violently. At 10:33 local time, 2 explosions crack across the desert. The X-1 had caught up with its own sound, sending a giant pressure wave crashing to Earth, the first sonic booms in the history of flight. The X-1 made aviation history. It also revealed the truth about the sound barrier. In fact, there was no definitive barrier at all. Unstable shock waves caused turbulence and drag in a zone of speed from about Mach 0.8 to Mach 1.2. At higher speeds, the shock waves stabilized and Yeager's flight once again became smooth and predictable. But what do shock waves actually look like? At Edwards Air Force Base, a NASA team sets out to take a picture of a shock wave actually forming on a supersonic aircraft flying high overhead. To make the image, an extremely powerful light source is needed, so they point their camera directly at the sun, hoping to capture pressure waves radiating from the aircraft as it penetrates the sound barrier.
Looks good.
A computer compensates for the Earth's rotation to keep the lens lined up with the sun. 6 miles high, the test aircraft now attempts to fly a precise course between the camera and the sun.
Initiate camera run now.
The airplane must pass through a target zone that is only 100 feet wide.
Steady on course.
Even with the best navigational equipment, it is a difficult task. This is one of only 2 photographs ever taken that shows a shockwave actually forming on an aircraft. It was taken by Ed Herring and the NASA team.
As we're looking at the sun, the aircraft flew by the sun, and we're looking at the light of the sun being refracted through the density changes of the shock waves. So we're able to see what the shock waves look like.
An aircraft's shock wave is like the wake of a boat. As speeds increase, the wake bends backward. To reduce drag, a supersonic aircraft must always fly within its wake. So as the planes went faster, they became long and slim, and wings were swept back. By 1958, only 10 years after Yeager's flight, military fighters were traveling twice the speed of sound. In that same year, a radical new aircraft was conceived. A spy plane, created in absolute secrecy to probe the enemy's defenses.
The experience with this program is it started out so ultra secret, you couldn't even tell your wife what you were doing or where you're going or when you'd get home.
Imagine an aircraft that could fly Mach 3, faster than a rifle bullet. travel further than any other military craft, cruise serenely at altitudes never before attempted. Such a plane would capture the high ground over alien nations and look down on them with impunity. But to achieve this dream, Blackbird's designers would have to overcome the objections of the atmosphere. First, the heat. At Mach 3, Blackbird would enter what engineers call the thermal thicket, a zone of speed where temperatures soar, 1100 degrees Fahrenheit at the exhaust, 800 at the nose. In extended flight, she would bake for hours at temperatures that would melt a traditional aluminum skin. To combat the heat, the plane's designers would use a rare and unproved alloy, titanium. Titanium could endure the heat, but was it strong enough to survive the stress of supersonic flight? To find out, they baked and stressed the plane in a giant oven at extreme temperatures. The test was reassuring, but how would titanium perform under the actual stress of flight? Test pilot Bob Gilliland.
The main concern, at least initially, was that this airplane had been built in a brand new metal. We didn't know exactly how strong it'd be. The designers had not done something right. The tail could come off, or something could break and experience a cataclysmic structural failure. So we were worried about that. At least I was, and I think everybody else was too.
As Gilliland accelerated past Mach 2, friction from the air baked Blackbird's skin. In her wake, the air boiled for 200 yards.
Everything's so hot. I remember I used to be able to put my hand up with a gloved hand with multiple layers and rubberized, and I could feel the heat coming in just from the heat of the glass on my hand up there, and so you wouldn't want to touch it.
On missions of 5 hours or more, Blackbird was subjected to what designers call a heat soak. The hot metal expanded, causing her fuselage to grow as much as a foot in length. But there was another problem. To go faster than Mach 3, Blackbird would drag a huge shockwave. Her jet engines would need the power of 45 diesel locomotives. And here, the designers took another risk. They built a revolutionary new engine that used an ingenious spike to harness the power of shockwaves. Aerodynamicist Dick Cantrell.
We reached Mach 3.2 at cruise, the shock wave forming on this tip of the inlet four-body spike grows and lays right here on the inlet lip at the face of the inlet, so that all of the air behind that shock wave, all of it goes into the inlet for maximum efficiency.
Inside the engine, the shock wave is bounced between the spike and the inlet wall. Air passing through the successive shock waves slows down, creating tremendous pressure behind the spike, over 40 times that of the outside atmosphere. That pressure actually drives Blackbird forward, providing 80% of the engine's power. As test flights continued, Blackbird ventured into new realms of speed. Mach 2, Mach 2.2, Mach 2.4. Suddenly, at about Mach 2.6, she showed her dark side.
Pilots have described it as something like a train wreck. It's kind of a wild ride up there for the first few seconds.
They were very violent, even under optimum conditions. They were very violent, and it would, when you're flying sideways, it makes the airplane buck around and bang your head around.
It was a sudden loss of thrust in one of Blackbird's engines that caused it to buck in the sky. The engine was too efficient, building up so much pressure that it blew the shock waves right out the inlet. The solution was a complex series of channels to vent the pressure away from the inlet and out the back of the engine. Only 17 years after Chuck Yeager had first encountered shock waves as he flew 700 miles per hour, Blackbird had harnessed the energy in them to fly 3 times as fast. The SR-71 flew into combat on missions so secret they are classified even today, over Vietnam, North Korea, some say even China and the Soviet Union. Even from the most dangerous assignments, Blackbird always returned.
I know I've heard that they've shot at it with the very latest Russian stuff over 4,000 times, and they've never gotten a hit. That speaks for itself.
Today, Blackbird still holds flying records for distance, altitude, and speed. With the advent of spy satellites and the end of the Cold War, no one has needed to better them. Of the 30 built, only 4 are still flying, and they are likely to remain the fastest military aircraft for a very long time. They are all descendants of 3 stallions brought to England from the Middle East 300 years ago. Their ancestors are shrouded in legend. But out of this legend comes an indisputable fact. In running a mile, no animal can outrace a thoroughbred horse.
Some of them is just like a bomb. They're ready to go off. It's not only just the muscle aspect of it, it's their own mind. They're really raring to go.
Careful breeding has created this magical mix of beauty, spirit, and speed. And to those who know, the sensation of riding a fast horse is almost beyond words.
Oh, it's a great feeling when they're running real good underneath you. Have you ever been in a car where you feel like you can go as fast as you want? That's what it feels like. It's a great feeling. Like I said, it's hard to describe, but I sure hope I feel it in the next race.
But the joy of a fast horse isn't just for jockeys. Horse racing is big business, but not easy money.
What you have at these major racetracks are 5,000 or 10,000 people at best, all doing their different handicapping, and that's why you will notice the tickets on the floor.
And the speed of thoroughbreds is changing. The fastest times haven't altered much, but the average has increased. Why?
Is we're getting better all the time in looking after them and taking care of them. Diagnostics are better now. Our therapies improve every year. We can catch problems when they're very small and remedy them before they become a cause for concern in the horse.
We're concerned today with detection in a very early stage of performance limiting factors which do not meet the eye and often are not visible on an X-ray.
This is the story of the search to understand speed in that miracle of motion, the thoroughbred horse. Suffolk Downs, a racetrack in Boston, Massachusetts. Today, the 2-year-old horse, Winlock's very own, will race for only the 4th time. Her trainer, Ron Dandy, is here to keep a watchful eye. Winlock's very own has shown some promise as a racer. She's trained well and has spirit, but in her last race, she finished poorly. After some rest, she is here to try again, and Dandy hopes to win.
There, if you're in front by yourself, fine. If somebody else wants
He consults with the jockey on some last-minute strategy. Often, these conversations revolve around the horse's personality. A jockey's job is to guide a horse through the best race the horse wants to run. Winlock's very own, number 6, is off to a good start. Here, she moves up to 2nd place. A burst of speed at the end will propel her to a win. But then, the opposite happens. She starts to slow down and fade. finishing a distant 6th.
Come to the last part when we really ask it to go, and when it comes to the running, it just kind of spits it.
Yeah, just like you got no horse under you.
That's it.
So you go from a lot of horse to no horse. Listen, I'll see you a little later, or I'll see you in the morning, okay? All right, thank you very much. I expected her to be probably, at her worst, be 3rd, and thought I had a shot of winning it. So
how do you feel?
Not too good.
Back at the racing barn, it's time for veterinarian Dr. Risa Sheehan to take a look. As anyone who bets on horses soon learns, there are many reasons for a poor performance. 1,000 pounds of horse moving at speeds between 35 and 40 miles an hour is ultimately a fragile machine. Everything from a bad start to muscle soreness can keep a horse from running well. A quick look with an endoscope, a fiber optic camera, reveals a symptom of Winlock's problem.
With the fiber optic endoscope, we pass right up her head, start here looking, and I can actually pass it to about this point down her trachea, where her lungs begin down here. And what we noticed was an amount of mucus discharge coming from her lungs traveling up her trachea. That's often a sign of what they call small airway inflammation. Inflammation in the lungs, mucus is produced, and it's cleared from the lungs up the trachea.
Dr. Sheehan suggests to Dandy that a further examination of the horse is in order.
She just can't finish up that way.
Well, that's, you know, he said it was a warm-up.
She refers the horse to a nearby clinic, run at the Tufts University School of Veterinary Medicine by Dr. Andrew Hoffman. He is on the cutting edge of research into the performance-limiting factors in racehorses. The first step in a performance evaluation is a general examination, essentially a search for clues. He pays careful attention to the horse's breathing. From previous experience and the description of Winlock's symptoms, there is already a likely culprit.
The prevalence of respiratory problems is very high. Of all the horses that are brought to us for performance limitation, for a decline in performance, like Winlock, approximately 50% of those horses have a significant respiratory disorder.
One of the weakest links in the creation of speed in racehorses is their respiratory system. When racing, their muscles demand extraordinary amounts of oxygen. They have to inhale and exhale at an incredible rate of 10 gallons per second. Even a small impediment to airflow can have disastrous results. So, as part of his examination, Dr. Hoffman uses an endoscope to look for any structural defect that might block airflow.
This is the glottis. This is the opening of the windpipe right here. This is the epiglottis and the arytenoid. And see how these arytenoid structures also, we call them curtains, open and close. Let's bring it in a little closer. Okay, come back. Okay, let's watch to see that these structures are opening and closing normally. Okay, everything looks pretty good.
This is what these internal structures look like now, while the horse is standing. But what about in a race?
Okay, we're done.
Dr. Hoffman can gain that view thanks to a technology not available to most veterinarians. A treadmill. Winlock doesn't seem thrilled at the prospect. But it takes a surprisingly short amount of time to teach her to go from a walk to a trot. To a canter. To a full gallop. By inclining the treadmill, a workout close to the stress of an actual race can be created. During such tests, the horse's heart is carefully monitored, but in general, cardiac function is not a problem. In fact, a horse's heart can handle a range of stress far beyond human capabilities.
A teenager running or training anaerobic exercise, their heart rate will get up to 160 or so, 170. Horses have a much greater incline in their heart rate from baseline before exercise at a heart rate of about 24 up to 210, so 9-fold increase in heart rate, something we could never achieve.
After a rest, the horse is outfitted with the endoscope, and the treadmill started. These are the inner workings of the main passage to a horse's lungs while it's at full gallop. A tape of the test is reviewed on the spot.
There we go. She's at her maximal effort here. She's got a wide open pharynx. She has perfect symmetry of her arytenoids, so her airways are wide open. She doesn't appear to have any physical obstruction to airflow.
The results are conclusive, but not enlightening. Winlock has no structural defect preventing air from reaching the lungs. Her poor race performance remains unexplained. Another test solves the riddle. A tube is inserted into one lobe of the horse's lungs. Then solution is passed into the lung and immediately suctioned out. The results will be examined under a microscope, but Dr. Hoffman can draw some conclusions just with the naked eye.
A lot of debris floating in there, and there's probably a greater density of the fluid than normal, which would indicate there's probably a greater number of cells and debris in this fluid. And of course, this is only a wash of a small segment of the lung. This is an indication that the entire lung may be full of debris. And of course, that's going to block the airways and restrict airflow.
The solution to the source of Winlock's problems is in here. The lab finds these cells, similar to those found in human asthma patients, indicating inflammation, possibly triggered by allergies. The cells are profuse and extremely toxic, but it's a condition easily treated with medications. However, is there extensive damage already done? The doctors at Tufts run one more critical test, which they were the first to apply to horses. This one checks the small airways inside the lungs by gauging their diameter and elasticity. The test works by sending oscillating waves of air through this mask into the lungs and then measuring the pressure wave that echoes back.
Okay, we got her centered, and now we're oscillating tiny little pulsations of flow into her respiratory tract. Now, you would think putting all these oscillations into the lung might be a little bit uncomfortable, but we have tested the system on ourselves and others, and you get a sensation of air moving in and out of your upper airways, but it's not an uncomfortable sensation.
After a baseline measurement, the next step is to introduce an aerosol of histamine. In a reaction familiar to allergy sufferers everywhere, it creates some constriction in the horse's lungs. If there is any airway damage, the histamine has an exaggerated, easily measured effect. And here, there's good news. Winlock's results are normal. The disease has not yet caused serious damage to her lungs. As if to prove the point, just 10 weeks later, after treatment, she ran again and won. Horses like Winlock are fortunate. With today's technology and early diagnosis, diseases can be stopped before they have a lasting effect. And that changes the outlook for speed at the track. There is no doubt that breeding and genetics have played a large role in the creation of a fast horse. But a new source of competition may be coming down the stretch.
We have selected for the elite horses, but that isn't to say that a lot of the horses that drop back due to performance-limiting disorders wouldn't come forward and break track records. I think until we actually understand what the limitations are to performance and deal with those problems very early in a horse's racing career, we'll never know whether track records can be broken again and again. I suspect that they will.
In the realm of molecules, speed is temperature.
All around us, we have air. Air atoms, air molecules buzzing around in the air. They're at room temperature. We can't see them, but they're traveling very fast, faster than jet airplanes, maybe 700, 800, 900 miles per hour. When you start to get things colder and colder, that speed goes down. And that's exactly what cold means for atoms. Cold means moving very slowly.
When Albert Einstein pondered how atoms would act if you could slow them to a near stop, he predicted that they would condense into a new state of matter, neither solid, liquid, or gas, more like a wave than a group of particles. It's been called the Bose-Einstein condensate. 5 years ago, Carl Wieman and Eric Cornell joined in a decades-old race to confirm Einstein's prediction. A race to create the coldest, slowest atoms in the universe.
If you go into your refrigerator, turn it down from, turn the cold from 2 up to 8. Let's crank up that cold. After your refrigerator gets colder, the little molecules of milk in your bottle of milk are moving ever so slightly slower. The air inside your refrigerator is moving a little slower. So for us, when we think about how we're going to get to these very low temperatures, almost to absolute zero, the question that we're really asking ourselves is, how do we make things go slowly?
Eric and his team have answered that question better than anyone by building the world's first successful Bose-Einstein condensate machine.
Okay, so up here really is just the staging area. This is just getting things ready. All the action really occurs down here in this glass cell as the laser beams come in from north, south, east, west, up and down, and push the atoms into a ball in the middle of the center of that glass there.
Step 1. Laser cooling. Photons emitted by a specially tuned laser bump into those atoms moving toward the laser source, slowing down the atoms and cooling them. In a fraction of a second, the 6 lasers cool a few million atoms of rubidium gas down to within 1/10 of a degree of absolute zero. In the lab, the condensate chamber sits at the center of a technotangle of coils, valves, mirrors, and sensors. Could this chaotic hodgepodge be the launch pad of breakthrough science? Ask the man in charge, Carl Wieman.
I have a very different approach to doing science. My approach is you think of the cheapest, quickest, most patched together way of throwing them together, and you see how it works.
One of the things that I noticed is that Carl is really cheap.
Frankly, there's a certain elegance. Anybody can spend $1 million and make some experiment work.
Carl is really cheap.
The really big way we save money is we use lasers that cost about $200 to $400 versus lasers that cost about $350,000.
While their competitors assembled million-dollar experiments, this team was making history with a machine cobbled together for under $50,000.
Just all thermal atoms, very cold, but just above the transition point where we go to.
But while their bargain basement lasers were shattering the coldness records, Eric knew that laser cooling could only take them so far.
Laser cooling is good as far as it goes, and I'd say about 5 years ago, laser cooling was the hottest thing in cool. I mean, this was just really the coldest anyone had ever seen, and it was very, very impressive. What we realized even back then was that it wasn't cold enough. We needed to get another 100 times colder after we finished our laser cooling.
To get the rest of the way, they used a phenomenon we all experience nearly every day, the cooling power of evaporation.
Actually, now evaporative cooling is the hottest thing in cool. It's the coldest temperatures anyone has ever seen, they've seen from evaporation. But it's also just about the oldest kind of cooling you could possibly imagine. The first cave woman took their cup of coffee off of the fire, and before they can get it to their lips, it's colder. And why? It's because it's evaporating.
The fastest moving coffee molecules go leaping out into the room, carrying away energy. And so that's why coffee gets cold. But you know, you also see this if you have just a room full of screaming children, and you take away the 2 or 3 that are the loudest, most rambunctious. You know, the average level of noise and energy goes down dramatically. And so that's really kind of the way our evaporative cooling works.
People talk about this place as the coldest place in the universe, but as fact, as you can see, I'm not even wearing a parka. Where the cold is actually happening is down in here, inside this little glass chamber. That glass chamber is like a thermos bottle. It keeps the atoms cold even though it's warm out here. If we could get down inside, in there, where the atoms are, that would be plenty cold. That's where we'd really feel the big freeze.
It's a big freeze at a tiny scale. Imagine these are a few million laser-cooled rubidium atoms that the scientists were pouring into the tiny container, a funnel-shaped magnetic field. Then they sped up the evaporation process by knocking the bounciest atoms out of the cup with a radio frequency field. The atoms that were left were colder than anything seen before, just about cold enough to begin seeing the Bose-Einstein condensation. But then the atoms began to disappear. The magnetic trap had a hole. Eric Cornell had a problem.
I had been working on it for about 4 years, on this project for about 4 years at that point. Finally, we were seeing evaporation. It was good, but it wasn't great. And it was clear that this trap wasn't going to work. And it seemed to me that it was time to stop fooling around, really start doing some major brainstorming on this, because if this problem wasn't going to be solved, we'd have to really take a big step backwards and really re-examine the way we were going.
Eric had an idea. What if they moved the hole around and kept it moving?
We can keep moving the zero, the point at the bottom of the trap around in a big circle. The atoms don't have time, they don't know what to make of it. They don't have time to react. They can't get down to that zero, so they can't find the hole. Instead, they're pushed this way and that way, and when you kind of add it all up, a little bit of push this way, a little bit of push that way, a little bit of push this way, in the end, it amounts to just pushing the atoms all in towards the middle, but to a place where the field's not zero anymore. The hole is plugged up.
Plugged up well enough to cool the rubidium to within 170 billionths of a degree of absolute zero. And right on cue, the Bose-Einstein condensate materialized. In the lab, the fuzzy speck on the TV monitor and the sharp spike in the computer readout
there it is.
Confirmed their accomplishment.
And we saw then the very, very small cloud of atoms appear, which corresponds to the Bose condensate. We knew those atoms, we could tell from how small the cloud was that those atoms were by far the coldest thing anyone had ever seen on this planet. And if you go out into interstellar space, everyone thinks, well, in space it's really, really cold. But it's not that cold, not nearly as cold as it was in that blob of atoms. When you get out into interstellar space, it's about 2 degrees above absolute zero. The atoms inside this glass cell were 1 million times colder. In fact, even more than that. So maybe there's a race of strangers out there, humans with big bulbous heads. I've seen them on the National Enquirer, and maybe they like to do atomic physics and cooling. And if so, they may have seen something colder. But if they're not, this was definitely the coldest thing anybody anywhere has ever seen.
Albert Einstein didn't need to see the coldest place in the universe to picture what would happen there. This confirmation of another of his predictions is a testament to his remarkable imagination. With nothing more than a blackboard and the power of his thought, he leapt across the universe at the speed of light and predicted the behavior of atoms at a standstill. Tombstone, Arizona. Home to legendary figures of the Old West like Wyatt Earp and Doc Holliday. A place where the myth of the gunfighter, the fastest gun in the West, lives on. "70 shooters from all over the U.S. have gathered here to find out who is the fastest gun alive. But they won't find out on Main Street at high noon. Instead, they'll face off in the last round of the championship competition in Fast Draw, the fastest sport in the world.
Shooter on the line, shooter, set.
Here's how it's played. When the shooter is ready, the announcer releases a button that will turn on a light after 2 to 5 seconds. The interval is random. When the shooter sees the light, he draws and fires a blank cartridge. If his aim is true, the hot gunpowder bursts the balloon target. The score is the elapsed time from the light turning on to the balloon bursting.
The amount of speed that's involved with this is mind-boggling. The world record to react to a light, draw the gun, and break a balloon is 0.208 seconds. 0.208 is faster than the blink of an eye.
Bam, you know, pow, like that. You're just moving so fast. Every muscle in your body is working. Stomach muscle tightens up, you know. You just pull and crank and pow and do that.
That light comes on, you've got to explode. And that's where I get my speed.
These shooters approach the limits of human reaction time, often beginning their draw less than 1/10 of a second after seeing the light. Practice, holster design, and talent all play a role in this duel of speed. And of course, there's tricks of the trade.
The top shooters don't look at the light. They don't wait for full brightness. They look at the filament of the light. When the filament starts to glow, they pull the gun and start drawing.
They have to study the light. They have to learn that light. And what I mean by the light is when that light comes on, it starts from the bottom and comes to the top and illuminates, okay? So you learn to watch that thing to make an instant reaction. When that's open, you move at the same time.
It's no accident that a Fast Draw championship match is held here. After all, Tombstone is the site of the most famous gunfight of the Old West, the shootout at the OK Corral.
Ready? Right.
But were fast guns really a part of the Old West? Or does the image of dueling gunslingers come from movies?
The gunfights like High Noon that Hollywood put out, you can count all the gunfights on the fingers of one hand. Because nobody did that, you could get killed. A novice could blow your head off. You had faulty guns or you had a bullet that wasn't any good. If you did that, you were dead. So you didn't get yourself into things like this. And when people back in the old days hired a gunman, he didn't go out and invite him out in the street and give him a fair opportunity. He just went out and shot him. That's what he was paid for.
So how would today's fast guns measure up against a legend like Wyatt Earp?
Well, if you put it up in this competition shooting at balloons, they would take the Earps and no problem. They're much faster. But the balloons don't shoot back. Now, if the balloons could shoot back, the Earps would probably come out on top. Wyatt Earp, his biggest asset was the fact that people knew that his first shot was going to be accurate and that his total objective was to kill him. Knowing that, fast guns don't mount a whole lot.
No one knows how fast Wyatt Earp could draw and fire. But there's no question he mastered a gunslinger's mindset. And though fast draw has gone through a world of change, the mental game remains.
It's mainly mental. It's mainly mental. I really work on my mental game, and I feel that that's the key, because after you shoot a few 100,000 rounds, you pretty much have the draws down.
It's down to the final round, and Cal Elrich is shooting for the World Fast Draw Championship. In this event, there are 2 targets. Cal must draw, cock, and fire, and then cock and fire again in under half a second. And he has to do it in each of 3 sets to win.
Shooter, set.
Cal's clean, fast shooting wins this tournament and secures him the title of the world's fast draw top gun.
Shooting, Cal. Thank you. How'd that feel? It felt real good, I tell you. Nothing feels better than that.